It'll be fun. You can just sit there and watch, bring something.
In like 20 minutes.
All right, well, yeah, that's what we're doing today. So yeah, y'all are talking about your classes have kind of dwindled down. Look at this class. It was full on the first day, right? Full.
I'm just happy it
So-
disappeared like a week before I was supposed to take it.
Yeah. So we need to finish up the solving equations. We did exponential equations last time, and I showed you a variety of problems. I can do maybe one more of those, and then we're going to get into solving logarithmic equations, and that'll be it. That'll be the last type, and then we're going to talk about the review. All right. So would y'all like me to start with a problem that covers the concept that we ended with last time, or are you ready to move into the next concept?
I'm ready.
What do y'all want?
Actually, can we go over like a little bit of the explanation?
Do you have one in particular, or you just want me to do one?
Just do one.
The last one we did was it the one 2 times 49 to the x?
Mm-hmm.
Yes?
Yeah.
Okay, I'm going to do number 71. This one's... What's interesting to me, I don't know if it's interesting, but it's this is the last problem. Number 71 is the last problem in this section when it comes to solving exponential equations. And normally the problems towards the end mean they're the harder ones, right? They start out with the easy ones, they get harder. And so I can't stop talking about calculus, I swear. I tell my calculus students day one that calculus is algebra on steroids, all right? The concepts of calculus aren't the thing that makes people struggle with calculus. The concepts are pretty easy. The ideas are easy. It's the algebra involved. So this problem would appear in a calculus class multiple times, something like this. So it's the hardest problem here, but it's just a problem in calculus. So let's at least look at it, all right? This is an exponential equation. How do we know this? Oh, the instructions are to solve, okay? Solve for x. So we know it's an exponential equation because we see the variable we're trying to solve for is up in the exponent. So what we've learned is that if we have something very simple, right? If we have something simple like 2 to the x equals 7, if we have something like that, it's very simple, well, not simple, but it's easy to use the logarithm to solve this. We convert this to log form, right? And we write log, whatever the base was here becomes the base here, and then we think about that loop. This becomes a 7, this becomes x, everything works out, right? The loop, 2 to the x is 7, that matches that. And then from here we use the change of base formula on our calculators. This is just natural log 7 over natural log 2 equals x, and we're done, right? We get that on our calculator, we're finished. This is still an exponential equation, but we cannot convert it over to log form. It cannot ever go into this form until over here you have something to a power equals something. Then you can do the log conversion. Here we've got multiple things, right? We've got 2 things over here being subtracted. This thing has a 10 in front of it. So I've got to somehow maybe get to that eventually, right? So when we look at this, the thing that you have to see that's hard maybe the first time you see this type of problem is that this is actually a quadratic form, all right? It may not look quadratic, but the one thing that would tip you off is that it has 3 terms. And quadratics normally have 3 terms. So what I'm going to do first is I'm just going to ask you to move the 3 over to this side, to the left by subtracting 3 on both sides, right? And then, oh, sorry, I forgot the negative there. Sorry, I need that. And then at this point, you're like, okay, well, I cannot, last class when we ended, I did a problem like this where I made a substitution. I said, let's let u be equal to, and you might want to say 4 to the x here, but see, this is 4 to the negative x, right? Not 4 to the x. That one's 4 to the x, this is 4 to the negative x. So these are a little bit, it's a little different, right? If you look at problem like 70, I think, yeah, we ended class with 70. And when we did number 70, what we did was we had that 7 to the x there, right? And what we did is we rewrote the 49 as 7 to the 2x. And then we were able to somehow use the quadratic. So let me just get to what we're going to do, okay? Let me just show you what we're going to do. I'm going to rewrite this as 4 to the x minus 10 times, watch this, I'm going to write this as 1 over 4 to the x minus 3. Now that's not crazy, I don't think, is it, right? Anything to a negative power is the same as 1 over that to a positive power? That's right?
Yes.
Also, I should point out, I mentioned last class, you can't multiply these together, right? Please don't turn that into a 40. You can't do that. Order of operations says you must do exponents before multiplication. If you don't know what that exponent is, then you can't put those together. Okay, so that's what we have, right? The next thing I'm going to do is I'm going to clear my fractions. See, you see that fraction? I don't like that 4 to the x on the bottom. I don't like that fraction. So I'm going to clear it. And to clear it, what I need to do is multiply both sides of the equation by 4 to the x. So I'm going to multiply the left side and the right side by 4 raised to the x. 4 raised to the x. Not 4x, 4 raised to the x. So let's do this. Let's do this first multiplication. What happens when you multiply 4 to the x times itself? I'll do that over here. What's 4 to the x times itself? If they have the same base, what do you do to the exponents? Add them. What's x plus x? 2x. So that's 4 to the 2x, right?
Wouldn't it be 16 to the 2?
No. Well, yeah, you could then rewrite this as 4 squared to the x, and then that could be 16 to the x. You could. Right? You could do that. But let's just leave it like this just for now, okay? So we get 4 to the 2x minus, okay, now let's multiply here to here. And what happens? That's the step that, this is why I brought the 4 to the x in. What happens when I multiply here to here?
Like 40.
They cancel out, right? The 4 to the x here cancels with the 4 to the x on the bottom, and all you're left with is what? Negative 10. You all right? You're doing 4 to the x times, let's ignore the negative, 10 times 1 over 4 to the x. That's what you're doing, right, when you multiply? And that cancel. And you're just left with that 10 that was there. So I have minus 10 there. And then the last multiplication here to here, right, here to here, minus. So yeah, how do you multiply it? You're doing 4 to the x times 3, right? You cannot, again, this is the same as 3 times 4 to the x. You cannot put the 3 and 4 together, right? Order of operations. So we have to leave it exactly like this, 3 times 4 to the x. So minus 3 times 4 to the x equals the right side, which is what? What's the right side of this equation? 0. Okay. All right. You all right with that? Cleared the fractions. Now, at this point, it's basically, did we do what number did we do here? Which ones did we do? Sorry. Did we do 62?
Yes.
Was it 62? 3 to the 2x plus 3? Okay, so basically we are at number 62 now. We're at something like that. So let me rearrange things. This is the same as 4 to the 2x. I'm going to move this one to the middle, minus 3 times 4 to the x minus 10 equals 0. So the reason I rearranged those is because now this is starting to look like a quadratic a little bit. This is like, how can I rewrite this so that it's something squared? 4 to the x, but then squared, right? That's what this means. Raising to the 2x is the same as 4 to the x to the 2. Right? Right? Minus 3 times, I don't need the parentheses, but I'll put it here anyway. just so you can see this is this. See these match now? See these are the same? And then minus 10 equals 0. Now, at this point, go ahead and make a substitution. Let u be equal to 4 to the x. Y'all look stunned. Are y'all okay? What's going on? You need to let me know. If you have a question, you need to let me know. Otherwise, this is one of the big lessons in college, okay? Especially in a math class. If you just sit there and say, I'll figure this out later, as you move up in math class, you're just going to get steamrolled. Okay, the train will leave the station and you'll just be like, wait. Okay, maybe that's already happened for you, but I'm just saying, like, you know what I mean? Like, you have to ask questions. Like, if you don't ask questions, then your professor's just gonna, at least I turn around and ask questions, like I ask you at least, right? Wait till you get to classes where your professors just say, here it is, go figure it out, you know? So, questions? Everyone? Now I'm going to substitute. Yep. No? All right. I'm going to make a substitution because when I squint my eyes and I look at this, I can see I've got something like u squared minus 3u minus 10 equals 0. So making that substitution, this becomes u squared minus 3u minus 10 equals 0. Let's just go back to the beginning, all right? I want to go through all this again. You see this initially, and you're like, whoa, okay, that doesn't look like a quadratic because none of these have a 2 on them, right? But then you realize that's a negative, that's a positive, so you drop it down. Then you clear that fraction out by multiplying both sides by 4 to the x. When you do that, you create the 4 to the 2x that you are going to need for the quadratic. And then the rest just, you know, is here. Then you have to rearrange so it looks more like this. Replace the 4 to the x with u, and now you've got your quadratic.
I'm confused on the rearranging part.
Okay, so I didn't have to rearrange here. I only did it because I wanted this line to look like this. If you didn't, then you would have had minus 10 here and minus 3u. These would have been backwards, right? And then you just would have rearranged later, maybe, right?
What if you combine though?
What do you mean combine?
Like the negative 10 and the negative 3.
You can't.
Can't?
No, because this is order of operations, right? So this is multiplication. This is an exponent. So you can't put those together, right? Well, you definitely can't put those together because this is subtraction. Subtraction comes after multiplication, right? So you'd have to multiply before you could do that. Is that all right? See, these are good questions, right?
You put it in parentheses, we don't get
Put what in parentheses?
3 times x to the 4th.
Put it in parentheses?
Yeah, just like.
You can, but that's kind of like over abuse of parentheses because it's not necessary. It's understood that you can't combine these, right? It's like if I write this down, 5 plus 2 times 3, right? You have to do what first? 2 times 3, right? You can't just say, oh, I'm going to make that 7 and then 7 times 3. That's why we have order of operations. So same thing here. It's kind of like you have a number minus all of this, right? But you can't combine those together because you got to do that first. And you can't do that because it's an algebraic expression, so you can't figure out what that is. I was thinking as I was walking to class, I was thinking about what would be my best advice to any STEM student. And that my best advice would be if you can find a way to like take a part-time job in the math lab tutoring, that's like the best thing you could ever do to strengthen your math. Because when you're tutoring things like what I'm talking about, what we're talking about right now, when you have to resolve all those little nuances of algebra and then help someone else explain it, then that means you know it, right? I mean, I honestly didn't get really comfortable with my math until I started helping other people. When I started helping other people, then I had to make sure I understood it myself, right? So anyway, okay. Shall we continue? All right, now here, what am I going to do? Factor it, right? I'm going to try and factor it. And we have, well, I could use quadratic formula as well, right? But I'm going to use that good old factoring thing where I did this thing, right? So we have negative 10 here, negative 3, your two numbers, negative 5, positive 2, and then you go through this mess, right? So let me just go ahead and write what it is. It's u minus 5, u plus 2 equals 0. So I'm not showing this work, just reminding you of how it's done. And then you set each of these equal to 0. Wait, oh, this was, yeah, well, I said plus, I wrote minus, didn't I? Okay, sorry about that. I'm still thinking about what I said. It's hard to remember when I felt uncomfortable with algebra, but I do remember it. Like, I do remember when algebra was scary, because it was all this stuff I didn't understand how it all worked completely. So the more repetition practice you have, the better you get at it. All right, here we are. Are those our answers? No, because we made a substitution, right? I mean, at the beginning of the problem, we're saying solve for x, and our answer is u, right? So we got to switch it back. So to switch it back, we got to go back to where we made the switch, and I erased it, but we had made the substitution u is 4 to the x, right? So I'm going to replace this u with 4 to the x, and replace that u with 4 to the x equals negative 2. Right? And this is 4 to the x, right? Not 4 times x. This is 4 raised to the x. And for this, now I can finally bring the loop in, finally, right? I have something to a power equals something. And so I can bring the log in. I can say log, the base of this log will be 4. I'll have a 5 here and equals x. And then I do that on my calculator, natural log 5 over natural log 4 equals x. I'll do that in a second. Over here, what can you tell me? No solution. Because you can never raise 4 to a power and get a negative number. You could also see it if you tried doing the log. You'd have 4 here, you'd have negative 2 here, you'd have x. And remember, the domain of any log, right? All logs, the number here has to be positive. Otherwise, it's undefined. So there's no solution here. And this one we do in our calculator and get the answer. What is it? 1.16?
Yeah.
1.16? Okay. 1.16. Okay.
How many did you get?
Well, I'm not sure that I'll give you something like this on the test. I would definitely give you something like this on the test. Definitely give you something like this on the test. I'm not sure if I would go here, but like I said, I showed you this because I know you're going to see this later. And there's going to be no like, hey, remember that? And you know, so I want you to at least have seen it.
I mean, it's basically the same. You just need to convert it to that.
When I see this, right? When I see this, what I think to myself is, that's 1 over 4 to the x. I'm going to have to clear the fractions. That's what I'm thinking. And then once I get to that, I go quadratic. Okay, so that was a. We'll have hopefully some time here to review a little bit, maybe get into some more of these. Let's move into the last topic that's going to be on the exam, which is logarithmic equations. Okay, logarithmic equations. I'm just going to call them log equations. What were those that we were just doing? What were these called? Exponential equations, because the variable was where? In the exponent. So these are log equations. Where do you think the variable is? Inside of a logarithm, all right? So let's start with something very simple, and I have examples here from the ebook, and then I have examples from the homework. So let's do the ebook first. I don't like any of those. Let's start with something really simple. Log base 3 of x minus 4 equals 2. Solve for x. Now, I think my opinion here is that log equations are actually easier than exponential, at least in the beginning. Because when you look at this equation, see your x is inside the log? When I say inside the log, this is what we call the argument of the log. I talked about that before. This is the thing that's being plugged into the log. This just tells you what the base is. So you're trying to solve for a variable, but it's trapped inside the log. The way we get it out of the log is just to use the loop. Just use the loop. What does the loop tell us here? This means we're converting it to exponential form. 3 squared must be x minus 4, right? That's what it means. And 3 squared is 9. And 9 equals x minus 4. We just add 4 to both sides, and we get 13, and we're done. We are done. Pretty straightforward, huh?
It's gonna get harder.
It's going to get harder, yes. So look, there's one little catch when it comes to log equations. You should always check your answers. Always. Always check your answers. So let's just check. And what we're doing is we're not checking to see if we get the correct answer. We just want to make sure that when we plug this number in here, we don't have a domain problem. So if I plug 13 in right here, 13 take away 4 is 9. 9's positive, right? Okay, so we're good. Just want to make sure that that number doesn't screw up the log, because if I plug that in and I somehow get a negative, then there's something wrong, right? All right, let's do another one. How about log base 3 of x minus 4 equals log base 3 of 2. This problem is so easy that it's hard. What I'd like to do is I'd like to show you a problem similar to this one, similar next to it, so you can see what I mean by how easy this is. 2 to the x equals 2 to the third. That's not the same problem. I'm just saying, look at this problem right here. Can you tell me what x is? 3. Why? They have the same base, right? So these powers have to be the same. So the answer here is x equals 3. Well, look at this one. This one says log base 3 of this must equal log base 3 of that, which means what? That has to be that, right? Okay, so that means x minus 4 must equal 2, which means x must equal 6, and we're done.
So that's the same as having.
This is like the exponential form of that problem. You just say, oh, just the exponents have to be the same, right? Here, since it's the same log, same base, the arguments have to be the same. You set the arguments equal to each other, and you solve it.
Like cancel the log.
It's kind of like canceling the log, but we don't really, we don't really say that. Now, why didn't we do that over here? Well, there wasn't a log on that side, right? There wasn't a log. So we did the loop, right? We did the loop. You could do the loop here, all right? But it's a waste of time. One of the beauties of math is that even if you do something a different way, right? You should get the right answer even if you do it some other way. Look, watch. If I tried the loop, what would it be? 3 raised to the what? Log base 3 of 2 must equal x minus 4. And if you look back at your properties from last time, what happens when you have a raised to the log base a of x? I forget what property this was. I think it was the third one. Maybe it was, yeah, this is just x, isn't it?
So it would just be 2.
So if I do 3 raised to the log base 3, these are the same base, then this just pops out and it becomes 2. And you get x is 6. So it would have worked that way as well, but I think it's, like I said, kind of a waste of time. All right. Pardon? If the base isn't the same, then we're, this can't do it.
Oh,
Yeah.
at all.
It depends, but it's not gonna, none of these are going to have different bases.
Oh.
Yeah. All right. Let's see. Let's try. I kind of like making them up, but I'll follow them. I'll follow theirs. Let me go back up. There was one here I kind of liked. Oh yeah, let's do that one now. Let's do 2 log base 5 of x equals log base 5 of 9. All right, be careful here. Oh, we never checked our answer. It was 6, right? I checked it mentally. I don't know if y'all checked it. Our answer was 6, right? And when we plug 6 in here, we get a positive number, right? So we're good? Okay. All right, look at that one. That problem over there, is that similar to this?
Yes.
There's log on both sides, same base, right? What's the difference? The 2 out front. We cannot right now ignore this 2 and be like, oh, then x must be 9, right? We can't do that. We have to account for this 2. So how do we account for it? Well, you might say divide both sides by 2, but then you're going to have a 1/2 in front of this one, right? So is there some other way we can handle this 2? Yeah. Exactly. We can push it up as a power. That was a property 6? No, 7. Look at your properties. Is it 5? It was the one I told to put like 3 stars next to it because we use it a lot. Is it 6? Yeah, go look at property 6. It said that if we had a power, we could bring it out front, right? Well, if we have something out front, we can push it back up as a power. It's a very nice, clever little trick. So this becomes log base 5 of what? X squared equals log base 5 of 9. Now you can do this. You see, because you don't have the 2 out front anymore. So I can now say what? X squared must equal 9, right? I can say that the arguments, right? These 2 arguments of the log functions, those 2 arguments must be the same. And then I solve that. How do you solve that? Square root both sides. And when you take the square root on both sides, you get plus or minus, right? Plus or minus 3. Plus or minus 3. Square root both sides. Now I have to check my answers. Go back to the original equation right here. Can I plug 3 in here? Yes, because it's positive. Can I plug negative 3 in here? No. So I'm going to throw away the negative 3. So my only answer is really x equals 3. All right. Let's look at the next one. Log base 5 of x plus 6 plus log base 5 of x plus 2 must equal 1. All right. Can we use a loop? Can we use the loop? Right now? No, why not? We have 2 logs, right? We have 2 logs equals a number. In order to use the loop, we have to have this. Log base something, something equals something. And then we can do loop like that, right? But this is a single log. We need a single log in order to use the loop. Yes? Yeah, well, you can put these together. That's what last class was about. Is that if you had 2 logs separated with addition, we have a property that allows you to condense them into a single log, right? And it turns into multiplication, exactly. So my next, what property was that? It was 4, but we're going to use 4 backwards, right? We're going to use property 4 backwards. So what I'm going to do is I'm going to put both of these into, hold on. Whenever I get an alert for a charge on my credit card, I always freak out. I've had so much fraud. Have y'all had a lot of fraud? No? Okay, that one's legit. Amber alerts. All right, putting these together. Log base 5. Okay, be careful on this. What we're going to do is going to turn to a single log, right? Equals 1. Now, what's in here are these 2 things, what? Multiplied together. So I'm going to put x plus 6 times x plus 2, right? That's what that is. Now, we have the freedom here. Do y'all want to multiply that out now, or do you want to wait? No. You want to do it now? Okay, so FOIL that out. Here to here, here to here, here to here, here to here. Combine like terms. I'm not going to show that step. I'm just going to show the final result, x squared plus 8x plus 12. That's what you should get there. Is that all right? I'm not showing that? Are you sure? Okay, now what?
Multiply both sides by log 5.
What do you have? Log with something of something equals something. The loop. Now you can do the loop. The whole purpose of turning the two logs into one is so we could use the loop. We couldn't use the loop here, but now we can, right? Now we can. Let's write that next line down. It'll be 5 raised to the 1 equals that, right? Let's write it down. So 5 raised to the first power equals x squared plus 8x plus 12. And 5 to the first power is just what? 5? Okay, what are you looking at? What do you have here in front of you? What is that? It's a quadratic equation. Do you know how to solve a quadratic equation? Get everything to one side, make it equal 0 first, right? So subtract 5 on both sides. 0 equals x squared plus 8x plus 7. All right? And now you have to solve that. You either use a quadratic formula or you factor. I'm going to factor. So this is where I'd be using that thing and going 7 here and 8 here. It'd be 7 and 1 and do my little thing. X plus 7, x plus 1, right? Set each of those equal to 0. I'm going to leave the original problem up there. If I set each of those equal to 0, I get x is negative 7, right? And x is negative 1. Anyone disagree? Is that all right?
Yes.
So far? Yes.
It can be.
Yeah, so we have to check these answers. Here's what you don't do. You don't look at these and say, oh, they're negative. I have to throw them both away. It's okay if these are negative. What you need is that when you plug them in, you don't get something negative. So let's try negative 7. If I plug negative 7 in right here, I get negative, don't I? That's not going to work. If I plug negative 1 in here, what do I get? 5. Negative 1 here. 1. That's okay. So that's our only solution. X is negative 1.
What if it was like -2?
Then we would say no. Then we'd have no solutions, right? If both of them, are you saying if both of them didn't work? Yeah, we just have no solution. Yeah. If it doesn't work for one, it's over. It doesn't have to not work for both.